loss in the fiber. And you know that when the signal is passing through the fiber, the material of the fiber cause absorption as well as the maybe the presence of the impurities or imperfections in the fiber that leads to the scattering, and that will result attenuation of the loss in the fiber. So basically, we now you know that the attenuation we expressed or unit of attenuation is decibel, and this is the attenuation curve. So, and we can divide this or classify the losses in intrinsic loss and extrinsic loss. And intrinsic loss is due to the material component of the glass, and extrinsic is that you can say during fabrications. Uh, there, in the during fabrication, the impurities will introduce and or a defect is created that came under the category of the extrinsic loss. So this is the attenuation curve, and this attenuation curve is only for the silica fiber, and you know that we have also plastic fiber. So this is not valid or true for the plastic fiber. This is only for the silica fiber. So in this fiber, we know that this the curve here, this line which is appears to be exponentially decay type curve, and this related to the Rayleigh scattering. And this curve is showing that it is at the Rayleigh scattering losses are more at low wavelength, and as higher wavelength losses are smaller. And there is this tail UV ultraviolet absorption tail, and this tail this tail is due to the electron transition. That electron will absorb the energy from the signal, and that results attenuation in the signal. And there is another case that we are using, for example, silica, so band gap is order of 8.9 electron volts. So that and wavelength corresponding to this wavelength is 140 nanometers. So if the signal around this wavelength, it will get absorbed by the electron, and they will go to the higher uh, in the say the conduction band. And there is another tail, infrared tail here. This is, and this tail is due to the when the absorption takes place by the glass molecules or say the silica. Uh, there is different because silica and oxygen they will oscillate or vibration. So there are different vibration modes. So when the transition among these different vibration modes, that leads to the losses in the signal, and these glass molecules, they will absorb the energy from the signal in the infrared region. And also if the material, if they have the impurity like Fe2 positive or Cu2 positive, the first type impurities, so they will also absorb the energy in this infrared region, and that leads to the absorption, and that is given by this line here. And another is we have this peak one here, another peak is this peak is this third peak is this around the 1360 nanometer, and this is around the 1250 like that, and this is between the 900 and 100 nanometer. So these all three peaks, they will contribute to the OH ion which are present in the fiber. So this is regarding the different contributions. So we will discuss in detail in next slide. So intrinsic loss. So as you know that intrinsic loss, as we talk about the UV absorption edge, and this exists in ultraviolet region, and this is we have discussed already that this uh, absorption edge, UV absorption edge, is due to the electron transition within the glass molecules, and tail is of this is extended toward the shorter wavelength of the fiber attenuation curve. So if we see that it is attenuated towards the shorter wavelength side, and we have the infrared and far infrared absorption edge, and that tail is due to the molecular vibration, the silicon oxygen bond. There is the modes, different modes. So absorption takes place, and this by this molecule, and to start vibrating due to the absorption of energy, and that will leads to the loss of the signal, of the attenuation in the signal. And there is another that, because for making the fiber we use the fused silica, and fused silica, the wavelength is out of band gap is order of 8.9 electron volt, and wavelength will correspond to this band gap. It is around 140 nanometer. So if the signal of order of this wavelength, it will get absorbed by the electron, and they will make the electronic transition. And another thing is that in case of air, because we are using the uh, silica, and it is in the fused form, and you know that if we have the crystalline material, so in that case what will happen, that this is the band structure. This is represent conduction band, this is the balance band, this is conduction band, and here band is sharply defined in the crystalline material. Whereas we have the amorphous, what will happen that, because we are using the fused silica, so this is amorphous structure. So what will that be due to in this amorphous? Here the the band uh, gap is not sharply defined in this case. If you see that here, this we got tail type thing here with the conduction valence band, and also with the conduction band, and this extended region leads to the another localized states in both sides, in conduction band, valence band, as well as conduction band, and this is results also due to the thermal vibration of the lattice ion. If lattice ion it start vibration, and that results to this, and also the material contain the imperfection or defects that leads to the formation of these band tails in the material, and these tails they are they also enhance the absorption of the signal, because now your band gap is also uh, extended, and we have more localized states are available. So the if the electrons or if the any impurity are present here, they can absorb the energy, or so that leads to the uh, uh, these type of in the UV absorption region, absorption takes place, UV takes. And infrared region, as we have discussed, that they are because the silicon SiO bond, they start vibrating in the infrared region due to the absorption of the light from the signal which are propagating through the fiber core. And there is also that not only absorption, but when the signal is passing through the core region, there is also attenuation, or the loss of signal is due to the scattering also, and scattering in the scattering is also wavelength dependent. So for example, in the core region we have random inhomogeneities. Random inhomogeneity means that there is variation in the refractive index, for example, in the small regions. Due to that variation, what will happen if the size of those inhomogeneities is smaller than the wavelength of your signal, then that leads to the effect which we will call Rayleigh scattering. And this Rayleigh scattering is dependent on the wavelength of the signal. If the signal is that the losses due to the Rayleigh scattering is inversely proportional to the Courte power of the wavelength. If the wavelength is smaller, it means losses are more. So at the low wavelength, the we are sending the signal through the fiber, the losses are huge due to this Rayleigh scattering, and we can't, they are unavoidable. But at a higher wavelength, the losses due to this Rayleigh scattering is smaller. So as the curve I have shown you, in the previous slide that exponential decay. So at the higher wavelength, the curve is the losses due to radio scattering was smaller. So this longer wavelength of light scatter less than shorter wavelength. And another is extrinsic losses, which we contributed due to this losses during the effects created during the fabrication process. So, for example, during the fabrication, what will happen that we will make the oxyhydrogen flame. So basically, it consists of oxygen plus hydrogen. So when to raise the temperature, and this we use for hyper cooling purpose. And due to this, what will happen that because we are using oxygen plus hydrogen, so that will result the absorption of water or OH ion in the core region or in the fiber, and that leads to the losses in the fiber because this OH ion will also absorb the energy from the signal. As we have seen in the earlier slide, we have three green peaks. So one was around 850, around 1200 nanometer, and around the 1300 plus nanometer. So at these wavelengths, the these OH ions will absorb the energy from the signal, and that results loss of or attenuation of the signal. And another is also that other than this OH ion, during fabrication, there are also Fe2 positive and Cu positive impurities. They are also present in the glass fiber, and these impurities, they will also absorb the energy from the signal in the infrared region. So there is another type of losses which we call microband. Microband means that this at the interface of core cladding, the surface of core is not smooth, you can say. It is very rough. A small bumps are present at the surface of this. So when we know that when you send the signal here, what will happen that here, the angle of critical angle collision will get disturbed, and due to this, what will happen that your signal will escape this core region. It will not go total internal reflection. So in this manner, if we have this type of during fabrication, if we have this such surface is created rough surfaces within this core, then this leads to the loss, and we would call such variation at the surface, we will call it microband. And another is band, macro band. So what is macro band? As for example, if we have this here fiber is state, so what is happening? The signal they are undergoing total internal reflection. Now at this region, we start bending it. If we keep on increasing bending more and more, what will happen that a stage will reach that here is again the critical angle condition will violated, get disturbed, and your signal will get lost. So while we are installing the fiber, we have to take care that how much how much amount we bend the fiber. So we have to take care because otherwise your signal will lost if we bend the fiber more. So we have to take care of this while we are installing the fiber. And this attenuation curve, we have three transmission windows. Means that transmission window means that we use, for example, we want to send a signal using this optical fiber or silica fiber at these three windows, 800 to 900 and 1260 to 1360 and 1500 to 16. And these three windows, here the losses are small as compared to the surrounding. So we choose the signal, send the signal through these windows. So, and we generally use the operating wavelength 850, 1310, and 550 nanometers for sending the copy. And another thing is that we need the light source for of those wavelengths. which lies between 800, 900 nanometer, 1260 to 1360 nanometer, and 1500 to 1600 nanometer. So we generally use the sources light emitting diode and laser diode, and all these they belongs to the infrared wavelengths. So generally, this 1500 600 nanometer window is today's standard long haul communication wavelength, and this window we further divided into different bands. And what are those bands? This is 1500 600 band. We uh, manipulated this window into different bands. So this first band we use this 1400 to 60 nanometer to 1530 nanometer, and we will call it a S band. If we use the operating wavelength in this region, we will call it, we are using in communication S band. And another window is band, you can say 1530 to 1565 nanometer, and we will call it C band and conventional band. And another band is 1565 to 1625. We will call it L band. Generally, we call long band. And another is the U band, and which is 1625 to 1675, and it is ultra long band, or generally we call it the U band. So this is all about the attenuation in the fiber.